This week on the Spotlight Report, I am really excited. I get to sit down with my friend Joel, not Joel.
Not Joel.
Joel Berkson, who got his PhD in optics somewhat recently from the Wyant College of Optics. And more importantly, Joel has started a company called Fringe Metrology, where he delivers pretty exciting metrology solutions for optics applications. And I'm going to let you speak more about that. So, why don't you tell us, I guess, how you first got into optics? Before we even touch upon your company, what made you go into this somewhat weird field?
Yeah, it was definitely on accident, and surprisingly, even growing up in Tucson, where there's this huge optics field happening at one of the best colleges for optics in the country. I didn't even know that I was there. Mm-hmm. And we were actually just talking that in high school, I had a physics class that I didn't really like, and I didn't even think I was going to do anything dealing with physics. I knew that I liked math, though. And so when I started my undergrad, I was kind of I started with just undecided engineering. I was like, maybe I'll do that. Maybe I'll do math. Maybe I'll even do neuroscience or something. I was kind of all over the place. But I remember the first engineering class, you had to go tour a few different departments. Mm-hmm. I didn't really think much of it at the time, but I had toured a few, and then one of the ones that I picked was optics, because my dad actually told me that he's like, I had this magazine about the College of Optical Sciences. It's really cool. You should check it out. And so I was like, okay, sure. So I just toured the facility, and I saw there was this crazy wide range of stuff people were working on, like these gigantic telescopes. People were working on holograms. Mm-hmm. People were doing laser stuff. It was just such a broad range of things. And so I thought that was really interesting. And so that's what I kind of just started with was, okay, sure, I'll start on the optics track. And then it kind of just kept growing from there. And every time I was thinking even maybe I'll consider another field, something would draw me back in, because it's just so versatile. There's so many cool things you can do for any application. Mm-hmm.
It's the catchphrase, right? Lights everywhere.
Yeah.
Did you know, I'm just kind of curious, did you know when you first were kind of exploring optics, that first year or the beginning of the first year, what any of it meant? At least for myself, I remember I talked to Wyant, he gave me a tour, and he's like, lights everywhere, it's awesome. We kind of what you just said. Yeah. There's telescopes, we do lasers, and it's great. And I was like, sounds great. I don't know what any of that means. Yeah. I know what it means, but I didn't have any tangible idea. Yeah. But what about yourself?
No, I felt the exact same way. And honestly, I don't think I really fully understood the fact that light is everywhere, and you start seeing it everywhere in real life. I don't know if you feel that way too, but I didn't. Yeah,
it makes you really popular at parties. Let me tell you.
It's I wonder how that works. And sometimes you have to shut yourself down so you don't kind of monopolize the conversation. But yeah, it happened to me a couple of years ago where I really just that was after many years being in optics, where I finally got it, where I could I might see something interesting happening just in nature or in the world, or in technology too, and I felt like I could kind of figure out how it must work. And so that was a really cool realization that happened for me.
Absolutely. There's the door peephole over actually on that door, the side of this house that's facing to the west, so the sun, when it sets, you get this cool chromatic aberration, you get this rainbow that forms on the wall. I remember when I first bought the house, I was like, that's cool. I'm not it's kind of weird. And now it's well, I know exactly what's happening. It's still not that exciting. It's exciting to me. So you went through undergrad, and then you joined the graduate program, still in University of Arizona. Yeah. What caused you to go to grad school?
Yeah, that's another good question. Even after undergrad, I wasn't sure that I was going to stay in optics at all. I had looked at industry, looked at just, getting a job straight out of undergrad. I had applied for a couple of other master's programs in different fields, in applied math fields, and robotics even. So just kind of all, I was, again, that was another situation where I was maybe I want to pull away from optics, but ultimately I decided to stay. And just kind of, once I realized that again, I had to remind myself that optics doesn't have to be just like one thing. You can do with it whatever you want. Mm-hmm. And I felt like I got like some reassurance with the program here that like I could have a lot of freedom to research what I wanted. And so that's ultimately why I stayed. And I also just felt like I still didn't understand optics at all. Even with a bachelor's degree in optical sciences, I was like, I still don't understand anything. So,
right.
And sometimes I still feel like I don't.
Yeah, well, it doesn't go away. At least not for me, anyways. So you joined the graduate program, and you eventually ended up in the same lab group as I did. Mm-hmm. But did you initially kind of search that out, or how did that work?
Yeah, I did kind of. I told our advisor, I was like, I'm going to like consider some other lab groups, not because I don't love this lab group, but because I was just, maybe there's other fields of optics that really interest me, and I just haven't even really thought about them or explored them yet. Mm-hmm. I didn't really explore them that thoroughly. I didn't really feel like I wanted to get into optical physics or any of the kind of photonic stuff. And so ultimately I explored for a very brief period of time. And then I realized that even with our advisor, I could still kind of research whatever I wanted with the support of an amazing group.
Right. Daewoo has enough lust for life or lust for optics that anything you're doing, he'll be excited about.
Exactly.
I think that's, I guess I want to kind of go on a tangent for a second, but I think that's important if any graduate students are listening. A lot of that early decision-making, at least for me, is not, do you want to work on deflectometry or fringe projection or something of that nature, metrology in general. It's more, how do you click with the advisor and the group? Mm-hmm. Is that kind of your experience? Okay.
Absolutely, yeah. And as long as they can level with you and they don't see you as someone who's like below them or somebody with less understanding. And I mean, ultimately, what ends up happening is the grad students know more about their topic than the advisor does. And that definitely happened with Daewoo, where like I knew so much about fringe projection, like he sometimes didn't even know like what questions to ask. Right. That's because how can you know everything about everything? Yeah, yeah. So yeah, I agree. Having like an advisor that's very open to what you want to work on, as long as it has some kind of application or some kind of real world use case, that's like super important. So I got very lucky that. I mean, I started with Daewoo in undergrad and then
you had him as an undergrad professor or just research with him? Just research with him. I didn't realize you were an undergrad at the time.
Mm-hmm. Yeah, when I first started, I think I was like a sophomore maybe.
God, okay. Yeah. Anyways, so your work, I mean, this kind of blends nicely to what you're doing now, but your work was in fringe projection, and that sounds pretty similar to your current company name, Fringe Metrology.
Yeah.
So can you kind of tell us what your work was on and how that guided you towards the company that you have now?
Yeah, for sure. My graduate studies, actually, my first 2 years, I really didn't work on fringe projection at all. I worked on a number of different projects, some optical design, so I did a lot of lens design. I worked on deflectometry for a little bit, for a couple applications. I worked with Hyung-Mo Kang quite a bit, doing some of his deflectometry experiments. And then I think one of the summers during COVID, I asked Daewoo, I was like, I don't really have a project for this coming year. Like, what can I work on? And he said there was this project related to radio telescopes, and that he wanted me to build an infrared deflectometry system for it. And I was like, in my head, I was like, "Oh man, this is really not what I want to work on." Like, deflectometry is really hard.
Complain enough about it,
and then I heard Henry complain about it too. Right. Yeah, and infrared deflectometry is just an even harder version of that. And then I was like, I didn't really know much about radio astronomy, radio telescopes either, so I wasn't really that didn't really excite me that much either. But I just decided, sure, I'll work on it. It's funding, and then I ended up having the best time working on this project.
And did you start with the infrared deflectometry? Okay.
Yeah, I built one, and I wrote a conference paper, and it kind of worked. The problem was that. And
sorry, I'm going to interrupt you. We should, for people listening, that weren't in the group. So what is infrared? What's deflectometry?
Right.
And why is infrared deflectometry particularly hard?
Yeah. So deflectometry is how you measure a surface by looking at how it reflects a known object. Mm-hmm. So just like Daywick always uses the funhouse mirror example, where you could put, a person that what a person looks like in front of a funhouse mirror, and then you see how it distorts that person, and without going up and physically touching the mirror, you can kind of intuitively know that the mirror must be shaped in this certain way. And that's essentially all deflectometry is doing, is just doing that in a much more quantitative way, and actually calculating, we have this known object, we have this unknown mirror, and we observe what the mirror does to it, and we can back out what the mirror surface is. And infrared deflectometry is how you get to perform that same process, but on a surface that doesn't look shiny. And so as you increase your wavelengths, like towards infrared, sometimes some surfaces will become shiny. And so that's where infrared deflectometry is really cool, is you could measure, like a machined metal part that isn't, would never work as an optical surface.
Yeah. And what else happens as you go towards the infrared? So
everything is emitting in infrared.
Right.
Everything, infrared is just anything that's hot or changes temperature is emitting infrared. And then also, everything is also reflecting infrared. So other surfaces that you wouldn't consider as mirrors, like an optical table becomes a mirror. Yeah. And so whatever your source you're trying to use to measure your surface is reflecting off of everything. And there's also no TV screens. So usually you'd use a TV screen or some kind of 2D pixel array as your known source. But with infrared, there's no screen, so you have to create that source somehow with temperature, essentially. And so that was a really tricky challenge to measure radio telescope components with infrared deflectometry. But we did do that. And it didn't work very well. It's very sensitive, as you know, but one of the most important parts about those surfaces is like measuring the astigmatism and like some of the lower order shapes. And that was just extremely difficult to calibrate for, especially since some of the panels were almost flat. They're just barely more curved than flat. So you need this gigantic source in order to, I had a ribbon that was like 1.5 meters long that I had on multiple translation stages that would translate all the way through one axis and then spin and translate through the other axis.
Yeah. What was it made of?
I used a nichrome ribbon.
Okay.
Actually.
Yeah.
Yeah. So that was really tricky. And so the way that was kind of like weren't.
And let me take a step back again. Why does this matter?
Right.
Like it's an astronomy telescope. We have telescopes all over. Why are you shining infrared light at them? Why are you measuring it? What are you trying to measure? Right.
So with radio telescopes, just like any other telescope, you want the surface that's imaging whatever you're trying to image to be as perfect as possible. The cool part about radio telescopes is they don't have to be as precise as optical telescopes just because the wavelength is longer. But the other challenge is you want to build a lot more of them, and they need to be a lot cheaper and larger. And so the radio telescopes the goal of them is to take more of an advantage of the economy scaling. As you build more of them, you want the price to go down, much more than optical telescopes. But so as you produce these surfaces, you need to make sure that they're the right shape so that when you go to image something, for example, like a black hole, which is where that event horizon picture came from, is radio telescopes, to make sure that you have enough resolution to see objects like that.
Okay.
And if the surface isn't perfect, you can't see things like that.
And when you say perfect, how perfect do you mean?
So usually for radio telescope panels, they're looking at lambda over 40 is like kind of the unspoken number, because there's so many error budget stack-ups in a radio telescope. Usually with an optical, lambda over 40 would be totally overkill. But with a radio telescope, you have all these different pieces that need to be aligned together. And so there's the alignment budget. Radio telescopes are totally exposed to the environment. So their temperature change is warping everything. Wind is vibrating and changing things, and there's gravity deformation. So the panel itself is a very small portion of the total error budget. So the panel has to be pretty accurate, even for centimeter or millimeter wavelengths. Okay,
and that lambda that you're mentioning, lambda over 40, is a longer wavelength than what we're used to in the visible.
Right.
So
yeah, much Yeah, much longer.
Okay. Okay. So stop me if I have this wrong, but we're trying to make something the right shape. We're trying to get that shape, the correct shape, to lambda over 40. And when you say the right shape, one obvious thing that makes sense is it's just curved the wrong amount. So it focuses at the wrong point. Or you said astigmatism, it's curved more in one axis than the other.
Yep.
I guess what dominates or what's most important for radio telescopes, or is this the case for anything? Do I just care about astigmatism or other shapes, I guess?
That's a really good question, and so far I don't have a definitive answer for that. And a lot of it seems that a lot of people in this industry don't totally understand that either. So where that lambda over 40 requirement comes from is the Bruce equation, and that tells you what the gain of your telescope is based on your surface RMS. Mm-hmm. Although that surface RMS is not based on spatial frequency at all. Mm-hmm. And so all of a sudden this equation makes no sense, because it's like your surface RMS, if you sampled 5 points, is going to be totally different than if you sampled every millimeter and sampled millions of points. So I've tried to use like something called the structure function before, which you've probably heard of, that's basically how you can define a requirement for a surface that's dependent on spatial size, to try to figure out what the requirements are. The problem is people who buy radio telescope panels and request them don't really define what that is either. You can kind of ask them, hey, like, what if I sampled this every inch or 2 inches? And they say, sure, sounds good. Yeah. It's kind of the Wild West of metrology in some degree, because the requirements are so unspecified. Yeah. But it does have an effect to some degree.
And I guess that's an important consideration for people outside of the field, is the requirements, whatever the customer tells you the requirement is. But at the same time, sometimes they don't really know.
Right,
exactly. And you might be aware of, well, it really is important to sample this or whatever. So, So I interrupted you quite a bit, but you were working on the infrared deflectometry system, and then it sounds like it shifted.
Yeah. So we were working on that system, and we realized it was just way too hard to implement in our lab space, because it takes up a lot of space. It took up an entire optical table at the time. And the research for that project was actually forming these panels using a flexible mold. So usually you would make the panels for a radio telescope with a permanent mold that you might machine out of steel or ceramic or something. You would put this piece of metal on it and heat it up and just kind of press form it to that shape. But then you have to, for every panel that's a different shape, you need a mold for every single one, and that gets expensive. And so that research project was, let's just use the same mold over again, but change the shape of the mold, and then we can just use the same thing over again. And so what became really challenging is that every time you change the mold, we'd actually want to measure it again with the infrared deflectometry system, which took such a long time. The mold and the panels.
Okay. Why do you measure both?
So you want to measure the mold so that you know so a big part of that research process was how well can we convert a mold shape to a panel shape? If we make the mold perfect and then we put a panel on it, does that shape imprint properly? Right. So yeah, it's like the same thing. If you can't measure it, you can't make it. So if you can't measure the part, but you also can't measure something along the way, there's just no way to know. And so that infrared deflectometry system was just way too hard to implement on that mold that was changing all the time, and we wanted to measure over and over again. There was a lot of iterations. So we used a different system. We used a ferro arm for a while. That's basically a handheld CMM, where you move this probe around and you touch points one at a time. And that worked to some degree also, but then you're limited to how densely you can sample a surface. It could take half an hour to measure a half-meter area with 1 inch or 2 inch sampling. Right. And only get 100 or 200 points.
And if there happens to be a little divot inside that 1 inch of your sampling,
you miss it.
Yeah. Right.
Exactly. And so actually what drove us to go to a different solution is our ferro arm broke. So our lab had like very limited funding, and our ferro arm broke. It was like a month out of warranty or something. And they quoted us almost as much as it would cost to buy another ferro arm to fix it. And so we had some like just webcams sitting around, and we had a lab projector. And for quite a while, I had been wanting to build a camera-based measurement system. I had worked at an autonomous vehicle company the summer before, and they used cameras all the time to measure stuff. Mm-hmm. I mean, they're looking at, is this tire 10 meters away or 10.1 meters away from me? So they're not looking at very precise things, but the concept is super, super scalable. And so I decided I would try to implement that same thing with just some webcams and a projector in the lab. I went through lots of iterations of testing different methods as I was reading papers and kind of getting up to speed with like where fringe projection was at. Mm-hmm. And then ultimately we were implementing a tool that was super useful for us, that we could measure the mold surface with very small spatial resolution in just a few minutes, and then iterate and kind of go through that process.
So why isn't this more often used? Or I guess even beyond that, why didn't you say at the outset, Daewoo, infrared deflectometry is going to be a real pain in the neck. Why don't we use fringe projection from the get-go?
Yeah. So I did tell him that, actually.
Okay.
But part of it was actually the grant that was for this radio telescope forming process. Part of it was money to build an infrared deflectometry system.
Okay, right.
And so we had to at least try it.
Yeah. So exterior constraints, I guess.
Mm-hmm.
And conversely, when your ferro arm broke, other constraints led you towards this.
Yeah.
So how did it work? Did it work well?
Yeah, it worked extremely well. So it's basically just based on stereo vision, which is as simple as that's how our two eyes are able to detect depth. You see an object on one place on your retina on your right eye, and a different place on your retina on your left eye, and your eyes know where they're located. Mm-hmm. And so you can just roughly extract like that's, a meter away or 2 meters away.
Right.
Usually because you know what the size of an object is. Like if you saw a ping pong ball, how big a ping pong ball is. And that's all that concept is. And if you scale all of the specifications and configuration of your two camera system properly, you can get to micron level resolution.
In terms of height?
Mm-hmm, in terms of depth resolution.
So this is, hopefully you'll humor me. This is something I know a little bit about, which doesn't always happen when I talk to people. And I know you pretty well. So let's go through the system itself. And to the extent that you can, let's describe kind of what the components are and what they're doing, and then how we're sampling or measuring that mirror.
Yeah.
So you said two cameras.
Yeah.
And where are they pointed?
Yeah. So let's ignore the projector for now.
Okay,
so like you said, there's just two cameras, each one pointed at whatever surface you want to measure. And that on each camera, that surface fills up ideally the entire field of view. And so then what you want to know is with two cameras, your goal is to triangulate a point. So just like your two eyes are detecting a ping pong ball at a certain distance, if you can detect one point on one camera sensor and say, that's the same object in my field of view on the sensor of the other camera, just in a different location on that detector. Mm-hmm. As long as you know where those two cameras are in space, tip, tilt, translation, you can triangulate where that point actually is on the object. Okay. So like if you put a smiley face sticker down, for example, and you see that on two different points on each sensor, as long as you know all those geometric constraints, you can measure where that smiley face is.
How well do you know those geometric constraints?
Yeah, so that's just known as stereo camera calibration. Okay. It's extremely difficult. Usually you'd use some kind of target that's already known, like a checkerboard, for example, where there's these white and black squares that are of known spacing in between each other. You would take a bunch of pictures of them, and then you'd actually reverse optimize what the geometric constraints must be in order to image this target onto each detector in this particular way. Okay. And so there's always some uncertainty in those geometric constraints. And there isn't a great way to validate them sometimes. especially because if you use a calibration target that it assumes it's flat, if it's not flat, that will impact and bias your calibration. If the square spacing isn't exactly what you think it is, that can impact it. If the temperature is changing and sometimes that can, and your material is made of aluminum, like that can change things too. And then there's even things like we use some distortion coefficients to characterize the distortion of each camera, but does that properly characterize, can you fit the actual distortion model of this camera to that model? Because there's so many different distortion models out there. So there's a lot of questions to ask there. We use some other methods to to refine that calibration even further beyond just a checkerboard, but I can talk more about that in a bit. So you have these two cameras, and you just want to say this pixel on this camera is the same on this object as this pixel on the other camera, and now we can say this pixel is this distance away. But you don't really want to put smiley face stickers all over your surface, right? Right. That would take forever, and smiley faces are hard to detect. Yeah. So
the customer wouldn't be happy. Yeah.
No, exactly.
Right.
And so that's where the projector comes in. And so what I had thought about doing is with deflectometry, we use this like pseudo fringe pattern, right? That's just a sinusoidal pattern. You go through some phase shifts and you get the wrapped phase, and then you unwrap it. And then you can say, oh, well, like I know which pixel is this phase on the screen, and I detect this on the camera. And that's, now you're doing triangulation with a mirror surface. So it's actually the same. I'm using the exact same technique as deflectometry.
Okay.
Where the projector is still going through a phase shift in X, a phase shift in Y. And actually what that does is it encodes the object instead of the screen with unique phase values. So then each point on the object has an X phase and a Y phase.
Right.
And the cameras see that from any perspective. And so then it just becomes a matter of matching this pixel has this X phase and Y phase. Which pixel on the other camera has that same X and Y phase?
Okay.
And then you can triangulate
that point. Okay.
So there's a huge search algorithm that goes through and does that for every pixel.
Okay.
So every pixel turns into a 3D point, basically. So if you have a 20 megapixel camera, you could have 20 million sample points on a surface that fills up the field of view.
Versus, like you were saying, okay, I'm going to touch the mirror every 1 inch and maybe get 100 points across, or whatever it would be for your optic.
Yep, exactly.
Okay. So a lot higher sampling, and then how... Let's ignore calibration and sources of noise and uncertainty for the time being. If everything worked great, or maybe if it doesn't actually, in the real setup, how accurate are you at pinpointing that point in terms of the Z height and not the XY? So we said we can sample it really great. How accurate is that height point?
So it depends on how big of an object you're measuring. On our system that measures a 1 by 1 meter area, we've been able to get to 4.1 micron RMS across the whole surface with that maximum resolution.
Yeah, that's incredible.
And we've done that on a grade A granite surface flat. So that's like the tried and true, NIST calibrated. It's we can trust it as much as we could anything else.
Right.
And that's the flatness that we're getting out of it.
4.1 micron RMS. Okay. Yeah, that's phenomenal.
Yeah.
So, and that includes low order shapes, like through everything. Yeah. Great.
Yep.
Yeah.
And that will actually lead in back to how we do the calibration is we do our rough calibration with a checkerboard. And then what might happen is we would measure a known shape, and there might be like some small low order shape error. And that the camera calibration pretty much only impacts low order shape up to like third term. Usually there's tilt terms, of course, but then there's just quadratic terms, and there's some cubic terms that show up, depending on if one of your cameras is tilted a little bit more than you expect. That's a cubic error usually. Okay. And we're working on kind of characterizing what each of those errors actually outputs, as people have done with deflectometry before.
Right.
And so we've been able to use a known target, like a granite surface flat, to actually reverse the calibration and say, let's optimize the parameters to force this to be flat. And then we'll measure the granite surface flat in a number of positions and heights, and then make sure that all of those samples produce a flat surface at the right size.
Okay. So somewhat global optimization more so.
Yeah.
Okay. And you mentioned, so that characterizes the cameras, and you mentioned that the errors tend to be low order errors.
Mm-hmm.
And I'm assuming part of that is we're pretty darn certain that the pixels on a camera detector, or we mentioned deflectometry with like a screen, we're really good at making pixels.
Mm-hmm.
And this is a tried and true lithographic process. So we know the XY spacing is going to be pretty uniform. We don't expect random distortions along that grid.
Mm-hmm.
So it's really more like the global bodies themselves.
Yeah.
Okay. What about the projector?
So the cool part is the projector does not matter. You can leave everything the same and move the projector wherever you want and retake a measurement without calibration. Because the projector is all it is a fiducial generator.
Mm-hmm.
It just is generating a phase fiducial. And that's all it's doing. So you could do that anywhere. It just has to be in focus to some degree.
Right. Okay.
Yep. There is the one thing you do have to calibrate with the projector. And a similar thing you have to do with deflectometry is calibrating the gamma of the screen. So you want your sinusoidal pattern that's an 8-bit 0 to 255. But all of these screens and projectors are not optimized to be linear brightness output because they're optimized for our eye. And so usually you would see something that's much sharper. Mm-hmm. Like you try to project your fringe pattern and it looks like bars, basically. Right?
Yeah.
The system actually, the cool part is it's not as sensitive to that as deflectometry because it's a fiducial. So actually, if as long as both cameras see the same fringe print through, they're just matching fringe print through to fringe print through, and it actually doesn't have an effect.
Huh. Okay.
If it's strong enough, it does though.
Right. So up to a certain limit, it doesn't matter. Okay.
Mm-hmm.
So for this project, it sounds like it worked really well, and now what you're getting out of it is you have dense sampling of your optic. You're getting extremely accurate kind of Z height. Mm-hmm. And was it, I guess there's one other thing. So for deflectometry, you mentioned it takes a bunch of space, right? Mm-hmm. How much space does this take up?
Yeah, so as long as you can put your projector in a position where it can fill up the surface and you can put your cameras in a position that they can see the whole surface, that's all you have to do. Mm-hmm. And so when you say how much space does this take up, it kind of depends on what lens you use and what sensor size you use. So we try to use the biggest sensors we can find, basically. Yeah. These big 24.5 megapixel sensors, and the shortest focal length we can find that isn't some crazy fisheye that's going to be really hard to calibrate. Right. And that's kind of the most we can get out of like the biggest field of view system from the closest possible distance. Mm-hmm. And so to measure, an area that's 1 by 1 meter, it might be a system that's a meter taller than that and roughly the same width. Okay. And then you can manipulate your projector wherever you can. And that's the cool part about the system. It's so flexible. You can just, any application, you just reconfigure everything and recalibrate and you can measure again. Yeah. And it's pretty reconfigurable and movable and portable.
And is it, so does it only test, sorry, what phrase this? Does it only test radio telescope mirrors? So, I'm imagining, at least in my head, I'm imagining a spherical dish, or maybe it's off axis or something. What shapes can it test?
So it can test anything as long as it fits, as long as you can get projected light on the whole surface and both cameras can see the whole surface. So concave stuff is pretty easy. Especially when you have your two cameras up here, and so the surface is kind of on one side it's pointed towards your camera, on the other side it's pointed towards the other camera. Convex is a little bit harder. You can imagine if it's curved like this and your camera is up here, the angle of incidence just gets really tight. Right. That really only happens for like very fast surfaces, like faster than f1, and sometimes they make stuff faster than that for radio telescopes.
But even things like freeforms or super funny shapes can be tested.
Yeah, there's no limitation other than like a full peak to valley height dependency where the cameras would just be out of focus at that point.
Right. So the surface itself has not only do you have to see the surface, but the surface itself must be in focus.
Mm-hmm.
Okay. Yeah.
And if it's out of focus, you can still measure it, but you just won't see the same spatial resolution.
Right.
I mean, even though you'd have a pixel, you'd get a point for every pixel, you would only be seeing 5 or 10 pixels kind of blurred together.
Yeah. Which, probably not what you want of different sampling veering across it. So, okay.
Yeah.
So it sounds like it worked out really great from that project. And then what happened after that? I'm assuming you learned some lessons, and I'm curious what those are and kind of how you carried it forward.
Yeah, so implementing that in the lab was, we weren't using the best hardware, we were kind of just using whatever we had we just needed to measure the surface, because if we couldn't measure it, we can't adjust the mold, we can't make panels on it, we can't test panels, we can't make telescopes.
Yeah, you can't graduate.
I can't graduate, exactly, yeah. I had to make something that would work. So, we learned a lot along the way of, how we make the system useful so that I don't have to sit behind a computer and run it every time. So part of it was developing it in a way that other people could use it more easily. Mm-hmm. And that's something we're still working on quite a bit. That's mostly what the company is working on is developing that to make it more user-friendly. But one of the biggest things I learned is at the time, so I developed this system for us, and then I was like, great, this is awesome. I wasn't even thinking about starting a company at that point. But then other people in Steward that are working on some other project, whether was a different radio telescope or pieces of glass or something, they had seen, walked by the room and seen flashing lights in there from the projector, and they're like, what are you doing?
Yeah.
And so I would tell them, and they're like, oh, I have this surface, can you try to measure it for me? And so then within 6 months or so, I had done tests for 3 or 4 different internal customers, basically. Mm-hmm. I did a measurement for the submillimeter telescope that they had a damaged panel, and they wanted to see how far that damage had propagated from, there was a point of contact around the corner, and they wanted to see if it rippled through the rest of the surface. So I was able to tell them, how much they needed to mask off, basically, and what part of the surface was still usable. And
that optic as well, for people listening, that optic is in the white paper, which is on your website. So we'll link not only to the company website, but to the white paper. And this is really interesting because you look at the picture, I guess at first order value, you look at the picture and you're like, yeah, it's damaged. I can see it. There's a chunk out of it. Right. But really what you're trying to qualify is, well, when do I not care, right? How far away from this thing that looks obviously bad is it okay? Is that accurate?
Exactly. Okay. So this panel was damaged on the telescope.
Okay.
And so they took it off the telescope, and because they had no idea if it, now how can they trust any of the observations after that?
Right.
Because what if this panel
found it? There's a black hole. There's no signal here.
Right. Exactly. Exactly. So they just they're like, we have to measure this thing somehow. Yeah. And they were trying to get a laser tracker. They were, they're trying to rent somebody's expensive system from somewhere, and really they just wanted to know, can we put this panel back on the telescope and continue observations in time? Mm-hmm. And so that's all we were trying to do. I wasn't trying to measure the whole surface, but I was trying to say, outside of this damage area, does everything still fit a nice low order shape?
Yeah.
I didn't even have to know what it was, but we knew that it was a conic of some kind. Yeah. So you can fit that to a low order shape, and so I was fitting the whole surface to that until everything kind of leveled out.
Yeah.
Which,
okay.
Yeah.
Right.
Which is
to be able to describe the conic it actually is. Mm-hmm. Okay.
Yep. So that was one of the internal projects, and then we used it to measure a mold that a project was making 30-inch telescope mirrors on. So this was actually for an optical application. So there is a steel mold that was very precisely machined. And then the idea was to slump a piece of glass on it to get very close to the shape. And then they were going to take that and polish it optically to get it as much closer. And they're spherical mirrors. So
yeah, okay.
It was so much faster to just get close to the shape, and then you don't have to remove that much material. Mm-hmm. And so I had measured the mold for them because from a CMM measurement, it wasn't meeting specs that it was supposed to, but they couldn't tell what was wrong with it. Mm-hmm. but when I scanned it with the Fringe projection system, there was such a dense spatial sampling. We were actually able to see the welding rib print through from the backside on the front surface, which they were spaced by a few inches, and you could very easily see this like kind of cross-hatched print through on the surface. It was only like 15 microns or something, but that was enough to have a pretty big impact. And so they were able to release the stress in the surface, and then they went down from 25 micron RMS to like 7 micron RMS, and then then they were slumping panels on, or slumping
they can
mirrors
proceed,
on it.
Right.
Yep. Yeah, so I had all these internal customers, and I was like, wow, okay, all these people are using it. Like, there's probably other people that would like to use something like this outside of industry. I mean, this is just a handful of examples in this building.
Yeah.
So then I started looking into starting a company and like, what can I really do with this? Is there a bigger market outside of radio telescopes, or is that still the best market? And so I went through a number of things to kind of figure that out. I did the NSF iCore program. Yeah. I don't know if you participated.
So yes, I went through that as well, and I thought it was really great. I'm curious to hear as well what you thought.
Did you do the national iCore program or the local?
No, we just did the local one.
Okay.
Yeah. Did you do national?
I did do the national one. It was a fantastic program, honestly. I got a lot out of it. For those who don't know, the NSF iCore program is a program that takes, if you have some research that you did in the lab at your university, or I think it's only from universities, actually.
I think so. Yeah. Don't quote me on that.
Yeah, me neither. I think that's the case.
Okay.
Everyone was from a particular university. You had some research you worked on that you think has real world applications, they'll give you some funding to travel and basically interview anyone you think might possibly be a part of this niche world of research that you've done, whether you think they're customers, you think they might be suppliers, they might be partners, whatever kind of part of that ecosystem that you see your research becoming a part of, you can kind of go understand what that ecosystem looks like and then say, is this the right thing for us to do? And if not, like, let's look at a different ecosystem and then look at that one. And a lot of times people will go through that project thinking that whatever they had developed is for this application, and then they'll figure out that would never work, and that they found something completely different that ended up being the right thing for them to do. Yeah,
and you were ahead of schedule, because I don't know if you were thinking this way already when you were doing these internal projects, but you were saying these are quote potential customers, right? Mm-hmm. And so you were already getting feedback from people that validates your solution that you developed. I think that's a really key part of iCore, what iCore delivers, like you said, but a key thing to internalize for anyone, and we'll get to this, we'll touch upon this in more depth later on, but for anyone that thinks that they want to start a company, the single first thing to do is go ask people what the problem is. Yeah. And there's a lot to it, and iCore can help a lot, but there's good ways to ask this without leading them to, oh, you have a problem, I have this, wouldn't it be great? Right. Because you might, kind of trick yourself in that process, I guess.
Exactly. And like a question for that, if I asked about Fringe projection, I would say, well, do you wish you had better spatial resolution on your measurements? Yeah. And of course they'll say yes, but they might not actually care. The question I should ask is, do you ever have a situation where you measure your surface and you don't know what's wrong with it?
Right.
And then if they say, yes, this happens, and I'll say, why do you think that you don't know what's wrong with it? Yeah. And then if that leads to them saying, we didn't have the spatial resolution, then that's the key information for me.
Right. Every customer always wants something more. Right. But that's not what you care about. It's what do you need? Mm-hmm. Right? Like what are you actually having problems with? Because that's really where they need a solution.
Right. So, and it's never specifications.
Yes.
It is specifications, but they don't know that.
Right. They're not going to write it out in, I need this exact thing, because they would have done it already.
Right. Exactly.
So you went into the iCore program, and you did the national one. So that implies that you traveled around to people to interview them. Mm-hmm. What did you learn? What did you get out of it?
Yeah, so I tried to start with, I knew that kind of radio telescopes was already a pretty good market, and so I was kind of reserving some of those interviews towards the end. If I tried a bunch of other things and it kind of failed. I went to mostly like factory automation trade shows and talked to a lot of those kinds of companies. to see if, there was a more of a rapid scanning, like maybe aerospace grade parts kind of thing.
Mm-hmm.
But I found that there was already a pretty huge industry for that, and they don't really have problems.
Okay.
I would try to ask them the questions like, what do you guys use to measure this stuff now? And they're like, oh, like this other company handles it for us. And, I would ask them like, do you ever have any problems? And they're just, no. Yeah. So I pretty quickly figured out, okay, this is just not the place to be. Mm-hmm. The other application was solar concentrators, because I'd actually used the system to measure a solar concentrator in the past, and it was useful for that.
Mm-hmm.
And so I interviewed some people at the National Renewable Energy Laboratory and Sandia National Laboratory, a few other places that work on solar concentration. And actually measuring the surfaces in production is the easy part. Mm-hmm. And they actually use something similar to deflectometry to measure them, which is interesting.
Yeah.
They have a gigantic version of it for them. And, but anyway, they had that problem solved, and actually their main issue was measuring them when they're already installed outside.
Right. Okay.
And there's just this huge field full of them. And so if you wanted to measure those, you'd probably use some other technique other than trying to set up cameras and a projector on every single concentrator. Right
tool, right job.
Exactly. Right? Yeah. Always. Yeah. Never. Sometimes you try to like force your tool to do something it's not designed to do. And that definitely happens. And I still catch myself doing that sometimes. Somebody will come to me and say, hey, can you do this? And I'll be like, maybe. And I'll try it. And then I'll be like, no.
We can. It doesn't make any sense, but we can. Yeah.
Like we can, like if I just like did X, Y, Z, W, like a bunch of things where it's like not even the same system anymore.
Yeah.
So anyway, so we'd interviewed a couple other industries, and then I kind of went back to radio telescopes again, and then got a bunch of great feedback from companies I was talking to, on people that managed the dishes themselves, and people that made the panels. And so actually what I found out most about from those interviews is one of the biggest metrology challenges for radio telescopes is aligning the dish outside. Mm-hmm. And so even once you've made the panels, which is what all of this fringe projection research was for, you still have to put them all together and then make sure they're all flush with each other. They're usually thin, so they are all bending in astigmatism and other modes. And they usually have actuators in the back that can fix that bending. Mm-hmm. But if you can't measure the whole surface, you have no idea what to adjust.
Yeah.
And so there was a few methods that existed to do that for radio telescopes. And people complained about that a lot. And so that's when I knew I was
For the alignment.
Okay. And so that's where I was like, it's not quite something we do for measurement right now, because we are working at 1 meter, maybe 2 meter surfaces at biggest. And some of these radio telescopes are 10 times bigger than that. It can be 20 meters bigger.
Right.
And I'm like, how do we scale this method to that size and like still sacrifice some accuracy, but still needs to be pretty accurate?
Yeah.
And so we learned so much from that. That's how we ended up writing our SBIR phase 1 proposal, was to work on a technology to measure the large dishes that are going to be built in the future.
Okay. Right. So you completed these interviews, and that let you write the SBIR paper. Before we even get to that, I'm really curious to hear how you felt doing the interviews.
Yeah, I definitely felt like it took a lot of trial and error. I mean, so through the ICRO program, you have to do 100 interviews in 7 weeks.
Right.
And like, that's a lot. They used to require that all of them were in person. Mm-hmm. Since COVID, you can do some of them virtually, but they started putting a lot more pressure on you to like really go do them in person.
Yeah.
And that's like 2 a day, and you're not going to be interviewing people on weekends.
Right.
And so you have to be scheduling these all the time with people, and you want to get enough time with people that they can answer all of your questions. Mm-hmm. So, I mean, how I felt during the interviews was I definitely like second guessing myself, honestly, and just being like, I would come out of an interview sometimes feeling like, this is a waste of time. Like I shouldn't be pursuing this company. Like I should just like think about something else. Other times I would come out of an interview thinking like, this is going to be my first customer. And then I would think back later and I would be like, I think I asked a lot of questions that were just like automatic yes questions.
Right.
And I think I biased myself into a hole. And then once I thought about it, I was like, I don't think they really need this actually.
Yeah.
And then every once in a while I'd have an interview where I was very honest and then I heard exactly what I was hoping to hear of like what their problems were. And then I would kind of tell them about what we were doing at the end, once they had fully told me about everything, all of their problems, so they weren't biased based on what I was doing.
Right.
I would even tell them, like, I'm just interviewing you to learn. Like, I'm not even working on a system.
Yeah.
That was, like, the biggest thing was, like, they would ask me why I'm doing this. And sometimes I would say, well, we're building a metrology system.
Yeah.
That's, like, then everything after that is a different answer.
Yeah.
Because they're
already biased. They
subconsciously, like, want to please you. They want to make you, they'd be like, make you happy. So I would just tell them, like, I'm just learning, like, and just totally detract from that. And then at the end, if it seemed right, I would tell them what we were actually working on.
Yeah.
So yeah, I felt very different depending on the interview.
I guess at the outset for me, I felt like it was really tricky. Mm-hmm. It's kind of hard to go, like I think at the first order, it's hard to go up to strangers and say, hey, can I talk to you?
Yeah.
About some kind of weird topic. Mm-hmm. And much less, beyond that, like you said, I think it can be really hard. Sometimes you talk to people and you're like, what am I doing?
Yeah.
Nobody needs this. I've talked to a bunch of people and nobody has said, yeah, I really have this problem.
Yeah.
And you can gas yourself up too of like, oh man, like this is going to be it. And it's not. And I think I think probably the biggest benefit of the interviews, whether you do them through the I-Corps program or otherwise, is you get that out of your system before money's on the table, right? Before you've really invested a lot of time or a lot of money on this thing that you think will be the greatest idea ever, you go and get some honest feedback.
Yeah.
And you, like you said, you kind of develop this network of people that could be your customer. Mm-hmm. So, yeah. So you I guess, do you want to respond to that before we go on?
I mean, yeah, that made me think of something too. Another industry I interviewed during that process was just like regular optics manufacturing companies. Like Colorado is full of them. They have tons of Rocky Mountain Instrument is there. Mm-hmm. There's a handful of others that they just make like standard optical components, like 4 to 6 inches and less, and mostly spherical surfaces. Some
visual optics,
visual optics, and some infrared as well. And then I was trying to think, like, is there a place for this system in just the optics manufacturing space? Do they want to measure the molds or the laps that they use to grind these optics down? If it was an A-sphere, like, it is transparent and specular, but what if we sprayed it with something and then measured it? Like, is that useful for them? Do they already have something that's good enough? And that was one of those situations where there was a time, where I would ask them the right questions, like, do you have an issue with any of your process? The answer would be no. Mm-hmm. But if I said, like, we're working on a metrology system that does X, Y, Z, they say, that sounds great. So
yeah,
that's where that bias comes in. So even though they said it sounds great, I know it's not the right customer.
Yeah. So, but it sounds like you got a lot of good feedback. You wrote this SBIR grant paper. I assume you got the grant?
Mm-hmm. Yeah, I just started last month.
Okay. Oh, great. Congrats. Mm-hmm. And so maybe more relevant is when did you start the company?
So I registered the company, I think it was 2 years ago now.
Okay.
So the fringe projection in general has been a concept for quite a while. Mm-hmm. I mean, I started the company name and website before I even did I-Corps. Mm-hmm. That was kind of when there was some internal stuff going on. And I wanted to get the domain name, and I was like, I wanted to pick something broad enough that if I switched to a different type of metrology, like, it would still work.
Yeah. That's thinking ahead.
Yeah, exactly. Get the right domain name and then go from there. I really wanted Fringe Technologies, actually. Yeah. Because then it could be anything. It is. Maybe I'll buy it at some point. Right. But at the time, a couple $1,000s for a website domain name, I was like, maybe someday. Yeah. But, so The company didn't really start doing anything until we went through the I-Corps program. Some companies that were in the I-Corps program were either still concepts from the university. Some of them were already registered companies, and we were one of those. We licensed the software from the university around that time also, which was also actually a great experience. I don't know if you've gone through working with them before, but
I've gone through on a few patents. I've never then licensed the patents from the U of A.
Okay.
So I've gone through the front end, but not the second part of it, which would be the more fun part of, hey, we're going to make money off of this. But yeah, so
yeah.
What is the software? Is it calibration or is it data processing or?
It's kind of the whole pipeline of the calibration and all of the data processing, and that just handles the whole metrology process.
Okay.
There isn't really anything. We didn't file for a patent, and we're not really planning to. Unless we develop something else. Mm-hmm. The system's all off-the-shelf hardware. You can go buy it anywhere. Yeah. And there isn't really anything super extra special we're doing to the hardware. It's just how we use it, basically. Yeah. And we could patent it, honestly, but sometimes patents can actually just expose you to people who see, oh, they're doing that. Well, let me do it a different way.
Right.
And then now all of a sudden you have this competitor that can do whatever they want. So that's why we decided not to do that. Yeah. But we still licensed the software from the university to have that good relationship with them, and we had developed everything in the lab there. Mm-hmm. And we are still doing things for university projects. So
nice, and they're customers now. Mm-hmm. Okay. So did you pursue? I guess did your solution shift? You were saying that one of the outcomes was that. System alignment, particularly for larger systems. Yeah. Did that bear fruit in the sense of, I guess in twofold, I mean, did that bear fruit, period? And then secondarily, is that your only customer now, or has it just broadened your customer base?
Right. So we have basically two main projects right now. One is the SBIR, and that's we're supposed to figure out a method to measure large dish outside to aid the process of alignment. Mm-hmm. And the thing we had originally proposed was doing this fringe projection system at a pretty crazy scale, where instead of 2 cameras, we'd be using like an array of like 25 or 30 cameras, and kind of looking at each sub-aperture and stitching it all together. And that turned out to be a really difficult problem. It's doable technically on paper, but really hard to implement. We're starting to move in a little bit of a different direction using a LiDAR system. So we're not just doing fringe projection anymore. We still do a lot of fringe projection stuff, but basically the goal of that project is we know that there's this problem that needs to be solved, and like we're not tied to using our solution that we know is the namesake of the company. Like we just want to figure out a solution to do that, and that's all that really matters. So we're exploring a different solution right now, and if that doesn't work, we'll kind of go back to our camera array concept and pursue that further. Okay.
Do you mind if I ask what domain you were stitching in?
So there's a few different domains you can stitch in. So we haven't tried it yet, but actually one of our other customer, we need to do stitching for that project. And so we're actually going to be stitching in the phase domain instead of the spatial domain. So you could, if you had 3 camera pairs that had an overlap, you could just make 3-point clouds and then stitch them together. But there's so many ways to solve that, especially for a surface that's pretty featureless. Yeah, that's just curved, right? But the cool part is if you use a projector that covers the whole surface, you could use phase to stitch all the points together. Right. Because the phase is the same no matter where you measure it from.
Right.
And so that's how we're going to be doing the stitching for that is in phase domain.
Yeah, stitching is a really fascinating problem, and I think if you haven't spent much time on it, kind of like everything that we're saying today, there's an enormous amount of nuance and subtlety to getting it right. Yeah. And it can be really easy to get it wrong, and the consequence of getting it wrong in any of this, whether it's stitching or just general metrology, is you tell someone, yeah, your optic is good, or it's not good. For classic example for like a visual optic is, this point right here is too high. Okay, I'm going to go polish on it. It wasn't too high. you've now polished a divot into your optic, or something of that nature. So,
yeah, that's the worst thing you can do is say your surface is wrong, and then give the wrong feedback, so they make it twice as bad.
Yeah,
and then that's
so maybe that's a good transition. Is what's the stakes? What matters here, right?
Right. I mean, the stakes are the whole point of measuring the surfaces in the lab, for individual panels at least, is to make sure that the right shape, so that when you put them on the telescope, you see see things with the resolution that you expect. And so the risk is if you don't measure something right, they take these panels out and they align them all. Let's say they don't even use our method; they use some existing method to align that works. And they go to image something and it looks blurry. And then it's like, then the risk is over time they go through and they try and figure out where the problem happened. Eventually, if it was in metrology, they'll get back to metrology. And just like it happened with Hubble. Right. Like the telescope got up there, it was images didn't look right, and they retraced and found that the metrology was wrong and they polished the wrong shape of the surface. The same thing can happen. Right. And so that's always the risk with metrology.
And we'll post a link to this episode. I interviewed Bob Parks, and Bob actually was part of the team that did the analysis to get to the issue for Hubble. And it's a really fascinating problem, how they caught it. We won't go into detail now. Yeah. But the stakes are, these are big projects. These can be they can be smaller, but they tend to be multi-million-dollar to billion-dollar projects. They tend to be multi-year endeavors. And like you said, man, at the end of the day, you don't want it to all get launched and get a picture and go, oh God, something's wrong, right? And that's a key part of the metrology process is, no, we know it's going to be right. Not only do we know the surface shape is going to be right, but we know that wherever it needs to be positioned, if that's relevant, also is correct. And it sounds like not only do you nail that with your system, but you kind of are sensitive to the nuance of that as well.
Yeah. I mean, hopefully, there's things. I mean, I don't want to claim that it's perfect. Things can happen in any metrology system that can cause things to be wrong. It can be user error. It can be calibration. It can be things can happen in the environment, like a camera gets bumps, or there's a large temperature change and some of the screw becomes loose and it moves. And so something else we're working on is ways to detect some anomaly has happened with the system. Like, we need to recalibrate everything now. Like, don't trust anything you measure from now on.
Something's gone out of whack. Well, that sounds fascinating. So I want to switch gears. I've taken up a good amount of your time. I'm going to take up a little bit more, and I want to switch gears. But before we do, for anyone listening, I guess, who should reach out to you if they have something to test, and then how do they reach out to you?
Yeah, so if somebody has something they want to test, any surface that isn't totally shiny, it can be a little bit shiny, and we can still measure it as long as it can scatter light to some degree.
Okay, so like a pre-polished optic, would that be?
Yeah, so and nothing that's transparent.
Sure.
We actually could measure an object that's transparent. We can spray the surface. Any kind of surface that you need measuring, and you're kind of looking at the 10 micron or less kind of scale. We can measure that at a pretty large range of sizes. The cool part about this system is it's so scalable where, right now I have this system that's like looking at a 2 by 2 inch area, trying to characterize the depth of scratches. And so we can do that. And then the same concept scales to a 3 meter surface. Right. And so whether you have something that's large, like on the order of, 5 to 10 feet that you want to measure, or it's some smaller part that you want to measure also, reach out, go to our website, or just find me on LinkedIn, and I'll be happy to consider even if that we could do it and try it for free. And at this point we want to learn what the capabilities of our system are anyway. And so
that website, we're going to link to it, but it's fringemetrology.com. Okay, so that'll be in the link as well. And should people, you kind of alluded to this, but in my experience, it can be incredibly valuable. Should customers or potential customers come to you if they're just trying to figure out what's important to measure?
Yeah, that's important too. A lot of times what people don't know, and this happened with a solar concentrating project we're working on actually, where they didn't know what the specification should be. This is a situation where instead of actually giving us surface RMS, they give us milliradian RMS. And then it's like, oh, well, that slope depends on your spatial resolution a lot.
Right.
Because if you sample 5 points, the slope is going to be crazy. But if you sample, it's super varying, and it really depends on what they're doing. And so we were able to just help them figure out what their specification even should be.
Yeah.
And so we have enough knowledge about optics that we can help with that also, beyond just like coming to us and saying, hey, we want to measure this with this resolution and tell us whether it meets our spec or not. But like we can like critically look at the spec and make sure that it makes sense for people also.
Mm-hmm. Awesome. Well, yeah, we'll add that link. So now I want to switch gears though, and maybe get on a more of your insights on starting a company, who should do it, why they should or shouldn't do it. So I don't know. What do you think? Is it worth starting a company? Looking back, kind of where you are now. Yeah,
I mean, I think so. What I really want people to do more, especially graduate students, because I started the company and was already thinking about it before I graduated, is there's so many graduate students I know that are working on amazing stuff. And, it might not be $1 billion company or $1 billion idea, but if they wanted a different lifestyle than, graduating and going to work for a big tech company, or even working for the government, if they wanted to have something that was a little bit different of a career lifestyle, they can take some idea that they're working on, and they don't have to grow it into the biggest company ever. They can just like handle their niche, whatever their niche is, and really enjoy that and just provide that for people. Mm-hmm. And so I think a lot more graduate students don't realize that might be a great avenue for them. But it actually is, and they just might not be exposed enough to entrepreneurship and what that actually means. In order to even know whether that's something they would want to do.
So you don't have to answer this if you don't want to. You don't have to answer any of these if you don't want to. How much money did you put in before the SBIR grant? Like what's the cost to you? Right?
Yeah, not that much. I had put in $10,000 of my own money into the company before the SBIR. And that wasn't really much. That was enough to buy enough stuff to build a demo system. Mm-hmm. That's the cool. The systems don't cost that much, so it's all off the shelf hardware. So we at least had a demo system we could show people. We went to one trade show and brought it with us to show it to some people. And that's all we really needed. And most of the I-Corps funding was for travel. And that's what we were spending most of our time doing, was going to people and just talking to them and seeing what their manufacturing looked like and how their current metrology was looking.
Right.
And so the reason you probably asked that is, how could a graduate student then put their own money into a business?
Right.
And I mean, I totally understand that. That was, a good chunk of the money that I had to put in the business. And the truth is I probably didn't have to do that. There's free money all over the place, it turns out. Mm-hmm. There's people literally waiting to give you money to do interesting things, whether it's through the university, the government, through private investment. There's all sorts of options. And I think a lot of people get scared of that sometimes. I mean, even a few years ago, just borrowing money from the bank wasn't the craziest thing ever.
Yeah.
Like, I mean, it's a little bit worse now, but in the past, you could almost borrow money for free as long as you were confident you could sell something.
Right. And I think that's something to consider for graduate students is, to some extent, if you do end up borrowing money, you're leveraging your future earnings power, which is large.
Yeah.
It's really hard to appreciate that when you're a student. Mm-hmm. I don't know about you, but it's really hard, or was really hard, to appreciate when you get kind of these first job offers of like, this is crazy. But you have this large future earnings power that you can kind of leverage. Mm-hmm. At the same time, do you need to? Right. So in my experience, we didn't need to invest anything. I mean, other than our time, because you do the customer interviews and you try to build the MVP, the minimum viable product, and that might just require sweat equity. Yeah. Right. In a lot of cases. Mm-hmm. So.
Yeah, depending on what it is, that can be the case.
Yeah.
And especially if it's at a university, what ends up happening is you can develop stuff, with their facilities on whatever grant you're working on, and just know that, when you want to license it, they'll take a small piece of it, but it's pretty insignificant.
Yeah.
And they did so much to help us. I mean, they did part of the package was doing some of our social media stuff. They built our website.
Oh, wow.
Also, the logo that we have came through the university and was part of that licensing process. Huh. And not other universities are different, but the University of Arizona is great at that, honestly. They've been amazing through that. And so you can almost see it as the university is investing money into you. Yeah. And most universities also have some kind of like slush investment fund that you can apply for. Mm-hmm. TLA has an asset development grant. Where you can propose to them an idea and they can give you like $50,000 to just do more research in the lab, and that's the investment right there.
Right.
That's not your own money. All they're asking is just like research this. That's not even a tie to saying you have to start a company or you have to license this.
Just try it out.
Just try it out, and then if you want to do it, they ask for a small piece.
I'd also say another thing that I've experienced and witnessed by other people is NRE charges, basically. So if you're trying to, you might get into some of these scenarios where you interview customers and eventually they say, oh, it's a great idea. We really need this. Like, we really need it now. Mm-hmm. And you know how to do it. Don't be afraid to say, yeah, it's not done. So there's NRE, there's non-recurring engineering, and it costs this amount. Don't sell yourself short, cover your costs. And I'll build a demo product. And go from there. So there's all sorts of avenues, I guess, to do this. Is it hard? Starting a company? Yeah,
I mean, it is. I mean, especially right now, I mean, I'm doing everything. I'm doing HR, I'm doing financing. I just did all of our taxes and went through all the books and made sure everything was going properly. And now I'm managing the SBIR grant, so there's like things to deal with there. We have another customer that we're building a system for, and that's like our first like really big project. Yeah. And they're kind of what you were just talking about, that the NRE part of a project is we had such an open dialogue with them where we're like, we're not sure that we can build this system because we haven't before, but here's how we think we can do it. And like basically we would need some money up front to try it.
Yeah. Which is a phenomenal deal for them. I think a lot of people don't appreciate that. It's really hard at a company to say, yeah, we're going to divert a lot of resources internally to this. It hoses everything up. Mm-hmm. If they can pay someone else to say, I'm an expert in it, yeah, I think I can do it. I'll try it out, divert some funds. That's a great deal. So
yeah, and that's pretty much what's going on. It's a little bit more like they want it to work. Sure, and it needs to work. It's more of a deposit than but that's basically why that they were okay with doing that, and like why the price tag was a lot higher than it might be if we already knew how to do it. Mm-hmm. If we wanted to build one again, like it wouldn't be as hard, and they might want more in the future. But this is what can happen when you're developing something that nobody else has, is people are willing to pay more for it or give you money up front to even try it. Right. Just because they can't find the solution anywhere else. They don't have any other option.
Yeah. Is it worth it?
Yeah, I think it's definitely worth it. There was a period of time where I didn't think it was, especially after you're going through grad school and you think to yourself, I've already given up the opportunity cost of working the last 4, 5, 6, 7 years with a bachelor's degree, and you start counting like, how much money is that? How much money do I make as a graduate student? Which wasn't very much. And then like that's the difference basically, and like what you're missing. Right. And you're like, should I just get a job and just like kind of cash in to like fight what just happened in the last 5 or 6 years? And I was definitely struggling with that for a while. Even like just a few months ago, I was like still like looking at jobs maybe, but I kind of like landed 2 big things at once, and all of a sudden was like, now I have things to do. Yeah. And I was very lucky, and I'm very fortunate that happened. But that stuff happens if you wait long enough and you're patient enough. And then it's totally worth it. Because if you do all the right things, something will happen. Mm-hmm.
It's totally worth it, even though it's a lot of work.
Yeah, it's a ton of work, but it's totally worth it. It's a lot of fun.
Okay. So I guess if you were looking backwards, would you have any advice to yourself or anything that you might have done differently?
Yeah, I think some advice to myself is I would tell myself to be more patient. There was a lot of points where I was like, I really just wanted to like jump into it like way too quickly and just like get down and dirty and build something. Yeah. That's what we do. Like, we that's what most of Daywalk's lab is like, we have an idea, like, let's prototype this as fast as we can and just like test the proof of concept. And every time I'd get an idea, I would just want to go do that. And sometimes, and I think I burned a lot of time doing that. Sometimes it ended up being useful, where like I would discover something helpful that would really help the system. But I think I burned a lot of time doing that. And so I would tell my past self, like, just be a little bit more patient and like really think things through a little bit more before I spend time. Is like the most valuable thing you have. You have such limited time, especially in grad school, and that's like the biggest free amount of time you can spend doing research. So I would just tell myself to be more patient.
Do you, I guess this is a general question, and you've mostly answered, so you do recommend, I think, if somebody has maybe a business concept, that they should pursue it to see, at the very least, if they want to pursue it more seriously, maybe. Let me phrase it like that. Do you recommend, this is a little pointed question, do you recommend grad school in general?
I do, actually. I mean, I don't know, you probably felt this way too, but after my bachelor's degree, I felt like I didn't know anything still. Like, I didn't understand how things worked.
That's correct, yeah.
Yeah, and like we just talked about, like, where it didn't happen for me until like a year or two ago, where I was like, I could really think about light intuitively. And I don't know if that would have happened for me if I didn't go to grad school and like spend all the time like really understanding things. So I would definitely recommend it, honestly. It was super worth it. And like, if you asked me a year ago, I might have said something different once, but you can never see the light at the end of the tunnel when you're in the tunnel. Like, once you're out of it and you look back and you're like, that tunnel wasn't that bad.
I've had a big shift in how I felt about grad school as more times passed on. But I think that's the tricky thing with almost anything, is it's a lot harder. It's hard to convince someone at the time, try to take away the positives, when at the time it might not seem like there's a lot. But
something I would like to encourage, though, because you mentioned, like, if somebody has a business idea in grad school, I would say like take it a step even further back from there. Like, what technology are you working on? Like, ask yourself, are there other people that would really like to use this? Or how can I make this in a way that somebody might really like to use? Like, just take the business part out of it, because sometimes that scares people. And just the grad students work on technology, so like let's like have them think about technology and just like, can somebody else use this? And then you go from there and be like, how can this be a business? So I'm just hoping more grad students start to think that way about what they're working on, is make sure other people can use it, and that whatever they're building, somebody else would really like to use it. And then everything can kind of go from there.
And I think that's a very different mentality than what comes naturally. I think, candidly speaking, most graduate students want to graduate, right? And so the thing that I'm thinking is, how the hell do I make this work so I can get the papers so I can be done? And it's an interesting, I almost think that might contribute to feeling maybe more stressed or more unhappy with your graduate work or research, is if you can't see the larger purpose of it, then it can feel really frustrating. Be like, this thing isn't working, and it doesn't really matter besides me completing something so that I completed it. But if you look at it more as, well, it's contributing to cool stuff, and that's great, and people want it to work, and this is exciting, I think, it can, like you said, it can make it a lot more rewarding and potentially open up some vistas that you might have not otherwise thought of. That's a
great point I hadn't thought about, is that just like, you're right, grad students, they want to graduate. And so a lot of times they're working on a project that's like, I just need to complete this so I can write papers and graduate. And that can be, when you're going through some problem while you're developing it, as everyone always does, when you're developing whatever research you're doing, it's like hard to keep yourself motivated. But if you do see that bigger picture, like you said, that can be a lot more motivating to get through it.
But again, easier said than done. Maybe.
For sure.
Well, this has been great. Do you have any other advice or anything else you wanted to discuss?
I don't think so. But beyond like reaching out to me or the company for whatever our company does, for whatever you might want measured, reach out to me if you want any advice about if you're in grad school and you have some technology you might want to consider starting a company about. If you want any advice on how that's been for me, or have any questions about that process, I'd be more than happy to give advice on that as well.
Perfect. Well, my guest has been Joel Berkson. His website is fringemetrology.com, and there will be links to that, as well as his LinkedIn and other resources on this episode.
Yep.
Thanks.
Thanks for having me.
Yeah, absolutely.